Time. It seems so simple, doesn't it? We experience it every moment. It flows, always forward, like a relentless river. Seconds tick by, turning into minutes, then hours. We plan our lives around this steady march of time. But is time truly as straightforward as our daily experience suggests? Physicists have delved deep into the nature of time. Their discoveries paint a picture far stranger and far more fascinating than we might imagine. The universe, it turns out, has some surprising tricks up its sleeve when it comes to the temporal dimension. So, what exactly is a time loop in the language of physics? Scientists refer to them as closed time-like curves, or CTCs for short. Imagine drawing a path through space and time. Normally, such paths always move forward in time. A closed time-like curve, however, is a special kind of path. It loops back on itself. If you could travel along such a curve, you would eventually return to a point in your own past. This is the theoretical basis for traveling backward in time. These mind-boggling possibilities arise from Albert Einstein's theory of general relativity. This theory describes gravity as the curvature of space-time. When Einstein formulated his field equations, he unknowingly opened a door. These equations under certain extreme conditions permit solutions that contain CTCs. It was a shocking revelation. The very framework describing gravity, one of the fundamental forces of nature, seemed to allow for pathways into the past. This suggested that the universe might be far stranger than even Einstein initially thought, potentially allowing for causal loops. Several theoretical constructs involving CTCs have been proposed. The mathematician Kurt Gödel found a solution to Einstein's equations describing a rotating universe. In such a universe, time travel to the past could be possible. Let's shift our focus to time dilation, starting with Einstein's special theory of relativity. Published in 1905, this theory revolutionized our understanding of space and time. It is built on two fundamental postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is constant for all observers. This leads directly to time dilation. Special relativity reveals that time is relative. Moving clocks run slower. The faster they move, the more pronounced this effect. From their perspective, their clock runs normally. This is the essence of relativity. For everyday speeds, time dilation is tiny, but at near light speed it becomes substantial. Particle accelerators provide evidence. Muons, created in the upper atmosphere, travel at near light speed. Their internal clocks slow down, allowing them to survive the journey. Section 4. Gravitational time dilation. Gravity's enduring grip on time's flow. Time dilation isn't just caused by motion, gravity also plays a crucial role. This effect is described by Einstein's general theory of relativity, his groundbreaking theory of gravity published in 1915. General relativity redefines gravity. It's not a force pulling objects together as Newton described. Instead, gravity is the manifestation of space-time curvature. Massive objects warp the fabric of space-time around them, and other objects follow these curves. This geometric view of gravity also predicts that time is affected by gravitational fields. General relativity predicts that time runs slower in stronger gravitational fields. The stronger the gravity, the more space-time is curved and the slower time flows. So, a clock placed closer to the center of a massive object where gravity is stronger will tick slower than an identical clock placed further away where gravity is weaker. This means that time passes slightly slower for people living at sea level compared to those living on a mountaintop. The difference is minuscule in our daily lives, but it is real, and has been experimentally verified with astonishing precision. Section 5. Space-time fabric, the universe's cosmic trampoline. The concept of space-time is central to understanding both time dilation and gravity. Before Einstein, space was viewed as a static, three-dimensional arena where events unfolded. Time was seen as a separate, universal clock. Einstein's theories merged these concepts. He showed that space and time are inextricably linked. They form a single, four-dimensional continuum known as space-time. Think of it as the very fabric of the cosmos, a dynamic entity rather than a passive backdrop. This fabric is where all events in the universe take place. To help visualize how space-time works, especially in the context of gravity, physicists often use the rubber sheet analogy. Imagine a large, taut rubber sheet. This sheet represents the fabric of space-time. Now place a heavy bowling ball in the center of the sheet. The bowling ball causes the rubber sheet to sag and curve. This curvature is analogous to how massive objects like stars and planets warp the space-time around them. The more massive the object, the deeper the curvature it creates in the space-time fabric. This curvature of space-time is what we perceive as gravity. Section 6. Interconnected realities, weaving time, space, and gravity together. It's clear by now that time loops, time dilation, and the space-time fabric are not isolated curiosities. They are deeply interconnected concepts. All these ideas emerge primarily from Einstein's theories of relativity. They force us to abandon our intuitive, everyday notions of space and time as separate and absolute. Instead, physics reveals a universe where space and time are intertwined, forming a dynamic stage that is itself an active participant in cosmic events. Our common-sense view, built from limited experience, simply doesn't capture the full, bizarre picture. Time dilation, both from special relativity due to motion and general relativity due to gravity, is a direct consequence of this unified space-time structure. When you move through space, it affects how you move through time. The faster your spatial velocity, the slower your temporal velocity. Similarly, the curvature of space-time, which we perceive as gravity, also dictates the flow of time. Clocks tick at different rates depending on their position within a gravitational field because space-time itself is stretched or compressed by mass and energy. Time loops, or closed time-like curves if they exist, would also be features of the space-time fabric. Section 7. The frontiers of time speculation, challenges, and the quest for unification. Time dilation and space-time curvature are well established, but time loops remain speculative. No experimental evidence supports closed, time-like curves. Theoretical conditions for them seem physically implausible. Paradoxes like the grandfather paradox pose significant challenges. The incompatibility between general relativity and quantum mechanics is a major hurdle. General relativity governs gravity and the universe's large-scale structure. Quantum mechanics describes atoms and subatomic particles. These theories make conflicting predictions in extreme conditions. The quest for a unified theory, or quantum gravity, is a major challenge.